Yeah, Computing Global Invariant Manifolds, Techniques and Applications. So that was the title that I chose for the proceedings paper that you're then allowed to submit in these 4 thick volumes. And so I try to convey more or less everything that I do, but that's too much to give in one talk. So I have some pictures here, and I want to address a little bit about everything. So first the setting. My work is mostly in the context of systems of ordinary differential equations, and so I really think in the form of vector flow. So I have first order differential equations. I have n of them, and if you don't like n, think n is 3, because most of the pictures will be in 3 dimensions. The vector field induces a flow, and I have all these definitions relative to what the dynamics is induced by this flow. So I have, for example, an equilibrium, right-hand side equal to 0. I have stable and unstable manifolds of this equilibrium. If the equilibrium is hyperbolic, all eigenvalues are off the imaginary axis. I can collect all the stable manifolds that lie to the left of the imaginary axis. The total number, if that's k, I have a k-dimensional associated stable manifold. And that stable manifold will consist of all the points in space that converge to the equilibrium. That's a saddle that's unusual. And so there's stable manifold theory tells you that there exists such a smooth object. Unstable manifolds, same idea, except that I go backward in time. And so if I have a vector field flow, I can reverse time, so that's all well defined. The picture that you see here is actually of the Lorentz equations, in case you hadn't recognized it yet. So there are 3 equilibria here, but the manifolds are drawn only for the origin at the bottom. The origin is a saddle with 2 stable and 1 unstable eigenvalue. So I have a 2-dimensional stable manifold and a 1-dimensional unstable manifold. And so in my picture, stable manifolds are always blue, and unstable manifolds are red. And so you see the red curve here that converges, if you want, or accumulates onto the chaotic attractor of the Lorentz equations. And I have this 2-dimensional surface, which is the stable manifold of the origin. And so again, if I pick a point on the stable manifold, I will converge to the origin. I don't go to the chaotic attractor. I just go to that equilibrium point. And similarly, if I take the unstable manifold, I go backward in time. Now you can see we have a vector field. This unstable manifold is 1-dimensional, so essentially that's a trajectory. And it's fairly easy to compute a 1-dimensional manifold, because all you need to do is find an approximate trajectory that represents that manifold. But for 2-dimensional manifolds, it's already a real challenge. And this is a little bit a niche. There are certain groups in the world who do this, and who are, I guess, becoming addicted to it. It's really nice to try get an even better picture of the stable manifold of the Lorentz equations. And so this survey article here that appeared even on the cover is a way of presenting all different possible ideas that people have invented to compute a 2-dimensional manifold using the Lorentz equations as the example. And you might recognize some names in the list here. There's a group at Cornell that was really interested in doing this. And so these are all different ways of trying to find an approximation of a 2-dimensional manifold. So not necessarily of the Lorentz equations, just of an arbitrary system, usually in 3 dimensions, but the dimension of the system could be arbitrary as well. So the way that I've been sort of advocating as part of my research is using continuation of a 2-point boundary value problem. And there are, well, maybe I should just go back a moment. There's the geodesic level sets that fall under that category that Bernd Krauskopf and I developed. And then there's also this whole setup in a more general way that was introduced by Sebius Duda. And so we have started collaborating, the 3 of us, and we're using combinations of the 2. So the whole setup is in the form of a 2-point boundary value problem. So you have your vector field. I'm using the notation U now. I've rescaled time. And I always think of U as being an orbit segment that starts with time 0 and ends with time 1. And the actual time is then the capital T here. That will be the end time. And so it's an easy trick. You formulate your vector field like so, and you can always think of having a 2-point boundary value problem set up where one endpoint is the condition where t is 0 and the other endpoint t is 1. Now the whole setup of what I use is on one end I restrict to a line, and on the other end I restrict to a plane. If you want a nonlinear curve and a nonlinear surface, but it's one-dimensional on one side, two-dimensional on the other. That's sort of the recipe. So you want to compute a two-dimensional stable manifold. Well, you find your equilibrium. You find the eigenspace associated with the stable eigenvalues. Then you're constructing your line, which in this case will be a closed curve in the stable eigenspace. That's just a linear approximation. If you're close enough to the equilibrium, we know that the real nonlinear two-dimensional manifold will be tangent to the eigenspace. So we can assume that that's a pretty good approximation of our manifold. And then we're looking for orbit segments that, I guess in this picture, start on this line and end, well, for example, in some plane sigma. If this is a stable manifold, the capital T will be negative. Easy setup. So you can do this thing in terms of a plane, which would be an implicit definition of, say, in this particular case, typically you would say take the z coordinate constant or something like that. But your two-dimensional plane could be defined in a more implicit way. For example, you could fix the integration time, that you just always have orbit segments with the same integration time, or you have a fixed arc length. Or a very nice trick is a product of arc length and integration time fixed. And so these are different techniques that you can use to implicitly define such a plane where you want to end. And can be used for computing, for example, the stable manifold of the Lorentz equations. But that's not the only thing. So what we do when we have these boundary value problems is that my endpoint on the line is something that I see parameterized by one parameter. And so I really would like to find a family of solutions to my two-point boundary value problem. And that way for that purpose, I use continuation. And the package that we use a lot is the package that Sabius Doodle wrote, because we collaborate with Sabius. It'll be hard to convince Sabius to do something else. And that uses the solution setup formulated in the form of a piecewise polynomial approximation of the entire solution. And the continuation is done as a sort of variational problem along the entire orbit segment, which makes it very stable when you have sensitive dependence on initial conditions or you have very different time scales. Now, Auto, as some of you may know, is also in some sense part of the XPP software by Bart Dummentraut, and you can set up these boundary value problems in XPP as well, so you could use that code instead. There is relatively later recent software called Coco that's developed by Frank Schiller and Harry Dankovic. That runs on the MATLAB, as does MatCont. MatCont has very much focused on discrete time dynamical systems, but the ideas of finding two-point boundary value problems are possible in the context of all these packages. So again, all the things that I show here are done in Auto. Now, manifolds, yes, stable manifolds, unstable manifolds, but you can do a lot more with this setup. And so this slide gives an overview of how I apply these ideas. And so there's certainly the transition to chaos in the Lorentz system. Those of you who went to the Oliver Club talk last week already found some of that, because Bernd Kraskopf gave a talk on all the things we do here, also in higher dimensions, not just for the Lorentz system. You can apply it in the context of systems with multiple timescales. There are several people here who work with John Guggenheimer, or perhaps others who are interested in systems with multiple timescales. Think of slow manifolds. These are not invariant manifolds in the same sense as stable and unstable manifolds of an equilibrium or of a periodic orbit or something, but they are, they can be computed in a very similar setup. And so overall these references are like the latest paper that gives you a good introduction into all the things that certainly I've worked on in the context of these computations. And so the Simon review paper is a very nice one of showing how these slow manifolds interact and give rise to mixed mode oscillations, for example. Now, more recently, I've gotten very interested in transient dynamics. How do you use dynamical systems in the context of finding transient behavior? Multiple timescale systems actually already fall a little bit in that category, because you have the transient slow epoch that is followed by a fast transition when you have, for example, a mixed mode oscillation. And so if you want to explain what's happening in the small amplitude oscillation part of the mixed mode oscillation, then you're talking about, in some sense, a transient phenomenon. So there is also isochrones, for example. You have a periodic orbit. You're trying to find out if you give the system a perturbation, how does it return to that periodic orbit? Isochrones are a kind of manifold, so you can use invariant manifold computation to find isochrones and explain how the system behaves under perturbation. How does it return to the attractor? Intrinsic excitability is a similar setup. The system itself in this context is often silent. And with Krasitsanova, who was also visiting last week, but she talked about something else, so that's not relevant. But Krasi and I work on models in neurobiology, and we're looking at bursting neurons, but these neurons only burst when they're coupled in a system. The neuron itself is silent unless you give it a stimulus. And so if you're just interested in what the system is capable of, you give one perturbation, not a constant input. And then you see how the system relaxes back to equilibrium. And so again, the dynamical system analysis would just say, okay, there's an attracting equilibrium. Well, that's the boring bit. How do you go to this equilibrium if you give your system a perturbation? And what options do you have? A stronger perturbation, does that give you a different relaxation back or not? Phase resetting in that context is the same idea. So related to the excitability and also to the isochrones in some sense. And here's a slightly different context, a very recent application that I've gotten interested in, doing this in the non-autonomous system. So you have a equation that depends on time. And you can still use the same computational techniques in that context. So I want to focus on two examples. One is from the phase resetting angle, and one is from this non-autonomous systems. And so that's what I will discuss next. So let's begin with the phase resetting. So this is work that I did jointly with Arthur Sherman. And we're interested in a particular type of neuron in your brain, in the hypothalamus of the brain. They're called pituitary neurons. This picture is a time series of an actual experiment of the bursting of the so-called somatotroph cell. And so this cover of the Journal of Endocrinology gives a picture of these cells in some enhanced colored way. And so you have the cell soma, and these brownish granular thingies are growth hormone that this somatotroph cell secretes. And the secretion process is known to be regulated by the kind of bursting pattern of the neuron. And so the interest here is in seeing how this neuron responds to a perturbation. And you should really think of this in the experimental setting. What can you do to this neuron? Well, you can give it an electrical current. And so you apply your current, and what you're observing then is some change in the phase. This is a bursting neuron. You give it a little kick, and then there might be a shift that the neuron bursts earlier than it would have without the perturbation, or it bursts later. And so that's what this phase resetting is interesting, is all about. And I should have maybe mentioned that this time trace actually is from the lab of Richard Bertram and Joel Tabak. And their main interest in, there are different types of pituitary neurons. How can you tell, based on such a simple experimental protocol, what is actually happening? What kind of neuron do you have based on what you're seeing in the phase resetting? And so Arthur Sherman and I really studied this in the context of a somatotroph cell, which is a very interesting model that, or a very interesting mathematical structure underlying this type of bursting. And so what you see is there is this sort of area here, which is the plateau where the voltage potential is ramping up. And then you get an epoch of a series of short bursts, relatively small amplitude, but at a high voltage level. And after Sherman had other people help with developing a very accurate mathematical model of this type of bursting. And so what you see here is a time series reproduced by a model of this type, Hodgkin-Huxley style. You have voltage, you have two gating variables, and then you have calcium. And so the influx of calcium into the cell and then the release of calcium is organizes this bursting here. And so as you are bursting high, calcium comes into the cell, and as you relax back, calcium is flushed out of the system again. Now this is a slow-fast timescale system. Actually, officially there are 3 timescales here. I have a very fast voltage, relatively fast gating variables, and very slow calcium behavior. And so the question now is, what happens if you would give this system a perturbation? And the main question was, what happens when you do this in the silent phase? You bring the system up to bursting. Because the experiments seem to indicate this is very hard. And you try to understand why. So the analysis here is very much in the style of John Renzel. Actually, he presented that work at a much earlier ICM in 1986. And so from that paper, he showed that you can look at what happens in your system, how it is organized by effectively freezing the slow variable. So you take your calcium and you just pretend it's not changing at all. So when you do that, you're left with a 3-dimensional fast subsystem, and you're getting calcium-dependent families of equilibria, periodic orbits, and the like. And so in this particular model, we have a silent phase, which is a family of stable equilibria for low voltage. And we have an active phase, which you could think of as a family of equilibria with a high voltage value. And so these blue ones here are attractors. I also have a saddle equilibrium branch, and there's a fold bifurcation here. So for low enough calcium, I don't have the silent phase at all. And for high enough calcium, there is a Hopf bifurcation that renders this stable branch unstable. And I have a family of periodic orbits that comes out of the Hopf bifurcation. Now this family of periodic orbits is not stable. It's a family of saddle periodic orbits. And that was very unusual. So this creates bursting, even though the upper state is an attracting equilibrium. So you would think that you're getting a relaxation oscillation, but what is happening is this type of pseudo-plateau bursting, as Arthur Sherman called it, where there is bursting generated by repelling or saddle periodic orbits. So the actual bursting you can now explain just from this bifurcation diagram in calcium. So the overlaid orbit here is the same time trace I had on the earlier slide, but now I have it in the calcium V plane, and I forget about time. And so the silent phase is tracking this lower state of equilibria, because in this particular case, calcium is decreasing. I will track this equilibria until I get to the knee. Then I've lost my silent state. My trajectory will shoot up, find whatever the attractor is somewhere else. You see the overshoot here. It starts the sort of oscillation towards this attracting equilibrium. But when now my voltage is much higher, calcium is increasing. And so I go past here, and as you see, even before I go unstable, I've gone through the family of repelling periodic orbits. I go out, jump back down, and the process repeats. So you can use this setup to investigate what the behavior of the system is. So can you also use it to investigate what happens if I give the system a kick? And so here, for example, if I were to set calcium equal to 1 and wait until I'm in the silent phase, calcium 1, boom, I give the system a kick. how does it relax back to this bursting orbit? What is happening to this system? Well, that's very easy. You need to give a kick to bring this. If you want to get the system to burst, you need to bring the system into the basin of attraction of that upper steady state. That should do the trick. So, okay, if I give a low perturbation, not high enough here, then I will drop back immediately. So it should be strong enough to bring me into this state. But this picture is a little bit misleading, because here I only show calcium and V. What I really need is look in my fast subsystem. I have a three-dimensional system. I also have these gating variables M and N. And so this lower equilibrium that I have for calcium equal 1 sits somewhere over here. And if I just go up, well, I don't find an equilibrium. The other equilibrium sits over to the right. And then there is this saddle equilibrium, that's this point here. And I have the family of periodic orbits, and for calcium equal 1, that's this closed curve here. Okay, so the question now is, how do I bring my system from this state, approximately, via perturbation, to the basin of attraction of that state? Well, the first thing, what is the basin of attraction? So what I did, or what I started with, was calculate the stable manifold of the equilibrium, the saddle equilibrium. And as you can see here in this animation, this stable manifold appears to separate the space in two halves. The silent state is at the bottom, and the active state is at the top. But then it folds over, and actually, when you think about it, it is not really the separatrix. It's not the basin boundary of the basin of attraction. It is an excitability threshold. And so here, if I stop the animation, I make my surface transparent, but I'm including the unstable manifold of this equilibrium, I see that the unstable manifold sort of goes below the surface straight away, goes straight to the equilibrium, whereas if I go a little bit above the surface, I will make one large excursion before I go back to the equilibrium. But this clearly indicates that the stable manifold of the equilibrium is not a separatrix. Both sides, you go to the lower equilibrium state. So the actual basin of attraction of this equilibrium, as you probably already figured out, maybe, is the stable manifold of this periodic orbit. There's like a tube there. This periodic orbit is of saddle type. It has a two-dimensional stable manifold as well. And so here I've drawn it in. It is sort of the, I don't know, it's the carton tube that the carpet rolls up around. Right? So this is like a carpet, and it rolls up around that tube. That's a weird tube, it's banana-shaped. So let's have a look at just this periodic orbit and its stable manifold. And so there are two views here. There's the whole thing here, well, computed up to a certain distance. And here I've chopped out a bit so we can look inside. And we see the attracting equilibrium here, now in white, and we have the lower state here. So I start at the lower state. I give the system a kick. I want to end up inside the tube. So the first thing you realize is you need to have a strong enough current, applied current. And so there is a bit of a study here in trying to find a good value. But if I have a strong enough current, what I see here is I will move away from the equilibrium. This is no longer an equilibrium the moment I apply the current. And if I hold this applied current, I will start moving towards another attractor. Now this attractor, as it turns out, does not lie inside the basin of attraction of the actual upper state that I have when I don't apply the current. So while the current is on, I move away. But as I move away, I will pass through this basin, in this particular case twice. And that's where the color changes to the cyan. There are two little segments here. And so I can see from this picture that I might have a chance, if I hold the current long enough, I might have a chance twice to be trapped by this basin of attraction of the upper state, and I will create a burst out of my perturbation. But it's tricky business. And so what I've shown here is using this theory of freezing the slow variable it's an approximation of what the real system does, but in this case it was actually successful, that it really predicts or helps predict how the system is going to behave. And so we found that there are two cases where you have a chance of perturbing up in the bursting state, and so we're giving a very geometrical picture of what is going on, but at the same time you're giving an experimental protocol on what you're supposed to be doing. Yeah, there is the actual strength and duration of the applied current comes out of this analysis.
So there's a reason you switch from current from voltage. You were talking about voltage before, now you're talking about current.
Okay, so voltage is one of my variables, and the current is the perturbation that I give. I'm applying a current which indeed changes the voltage.
Gotcha.
Yes, I'm sorry, I wasn't.
But the resistance is current assumes constant or
Yes.
okay.
This is a living cell,
Right.
or
So I'm wondering.
assumed still alive, and then you're hitting it with an electrode, and you just it's
Okay.
applying
Thank you.
an electrical current. Yeah, that's what's happening. Yes.
So, as a measurement of how hard it is to actually get captured in the basin of
Yes.
reaction of the other one, you need to look at the ratio of the duration of time you spend within the basin relative to the length of the trajectory up to that. I'm suggesting a criterion for how hard it is to achieve.
Yeah, I guess in this context, the fact that it is hard is because most experimentalists or even the modelers who were trying to do this on the computer were thinking in terms of like, I give a strong enough kick and I hold it for 3 milliseconds. And then they were just playing with the strength, not realizing that the 3 milliseconds might be too short for this case.
Or too long.
Or too long. And so that was a very important ingredient that explained why it was so much harder. But I guess, your ratio, there is certainly a relationship between giving a stronger current and having a shorter time. And there's like a little band of options. Actually, for you, it'll look like this. And there are two such bands. The other one's much thinner, just as you can see that here in this little segment. Okay, so let me go to the second example, which is actually in the realm of civil engineering. And I've been working with mostly civil engineer Nick Alexander at the University of Bristol, where we consider, these are experiments of a particular type of building structure that is behaving better when an earthquake were to hit. And so the idea here is that you're having cast concrete blocks, and there's these reinforced steel in there, and these steel poles of beams, they're connected, so the horizontal beam is connected to the vertical beams via a steel cable that's stressed. And so it's like a stressed spring. And so what happens if an earthquake were to hit, this building starts shaking and the frame starts shaking, and then the connection acts as a hinge. So the horizontal and the vertical beam will effectively open, there will be an angle there, and that allows for a larger excitation, larger tilt angle of the building. And then once the earthquake has passed, and it wasn't too bad, then the building will just snap back into position, and there is no structural damage to the frame. And so that's a trick. It's actually a building technique that is used, it's quite popular here in the US. And there have been a lot of experimental studies on how this building behaves under all sorts of earthquakes. California 1929 being particularly favorable as a test earthquake on the shape tables. So it's a nice toy, but I don't know, civil engineers, they really like to build up and get these concrete things and then shake them until they destroy or whatever. But anyway, so here Oliver Bjornsson has been doing a lot of experiments trying to find out the real behavior of this building in a more mathematical sense. And this paper here in the Journal of Sound and Vibration gives a model, an actual system of equations that describes the behavior of this building. And it's all based on using a sine wave as the earthquake. And so the experiments have been done really testing and matching parameters with the experiments, but also using first principle to derive the equations. And it's very nice. What's really nice is that this building has a frame. You have several rooms if you want, several stories. As long as you allow a certain amount of symmetry in your building, then you can just treat it as a single rocking block on an elastic foundation. And so the equations are remarkably simple. And here they are. It's really just a pendulum equation. I have a damping term and a stiffness, and that's my earthquake. And so the stiffness is a nonlinear function. It's actually linear in this regime, -1 to 1 for phi. Phi you should think of as a tilt angle of the whole frame, but it is scaled so that when phi is equal 1, that's when the hinge opens. And in this particular construction, you're allowed 10 times that tilt angle, so the hinge is already open the moment you go past 1 or below -1. Then you can go up to 10 times that angle, and you will still be structurally safe. It's only after you go beyond 10 that you're in trouble. The building may still be standing, but it's not safe to go back in. Okay, so that's a very interesting, it's just a nonlinear damping term on the identity. So it's the identity between -1 and 1. Okay, so I'm fixing this gamma, and I'm going to fix this omega, which is the frequency of my earthquake. And the damping term is realistic for the building that was on the earthquake shaking table. This frequency is sort of close to the way the nonlinearity has changed the peak of the natural frequency of the building. And so you could think of that as a bad case. Okay, so I'm going to see what is happening when I change the amplitude of my earthquake. And so here is a picture of what you could do. You have your model, you have your time equals 0, the earthquake is about to start. You have a number of initial conditions in the phi and phi dot plane, and you could just integrate, do brute force simulation, find out whether you're going to hit 10 or -10 or you stay inside. If you stay inside, everything's good, color white. If you go out, you color according to the time it took before you left. Blue is actually really fast. So my time that it takes goes from blue via green, yellow to red. And you can see here it goes very fast. In this particular case for A equal 0.6. A good trained eye will see slightly lighter blue colors over here. I will get to that. So
T equal to 0.
Sorry?
T equal to 0.
So T equals 0 is this particular plane. So my parameter space, I have a non-autonomous system here, so I have phi dot in T. I'm taking the slice T equals 0. So these are initial conditions at the moment that the earthquake starts, and I can see what's going to happen. And the civil engineers tend to see this as their phase space, but that's not exactly true. It is a slice in this phase space. Now you can see here, if I start at a large angle, and I have a relatively large velocity, well, my angle is positive already, my velocity is also positive, so boom, I'll go to, for you this way, to +10, right? And my building, I'll certainly keel over if I do that. So the building will probably be destroyed. And similarly, if I have a large negative angle and a large negative velocity, I will go out through -10. Now what happens at the boundary here, you can imagine, would be an event of grazing. I'm about to get to 10, but I'm just getting to that boundary. I have velocity 0 and I move back in. And so these are called grazing orbit. I have two types here. If I start at some angle and I get to +10 angle, but with 0 velocity, I graze. I could say I've reached the extremes of my design, but this is still allowed. I go back in. Similarly, here's another example where I start with some angle, and there's an associated velocity with this, it's not shown in the picture. I will go, I actually miss +10, but then I touch -10, but just tangentially, my velocity is 0. So I have right grazing and left-grazing orbits. And this boundary, where I go from blue, if you want, to white, that particular boundary you could think of as being formed by these families of such grazing orbits. These are the initial conditions where I precisely touch +10 or -10 for the angle. And then I thought, but I can calculate that directly. I can set this up as a boundary value problem. All I need is start with an initial condition in a plane, and I'm going to end on phi equal 10 with velocity 0. Yeah, I'm doing this, that's phi equal 10. But velocity is 0, it's a point, but it's arbitrary integration time. So it's a line. So I start in a plane, t equals 0, that's one boundary condition. And the end condition is phi equal 10, velocity equals 0, and t arbitrary. Brilliant. That's a boundary value problem. I can calculate that. So I can find this one as a family by just changing, well, I change the integration time that it takes to graze. And I can find this one as a left grazing family. And so that's what I did. Great, problem solved. Except that it looks a bit weird. I have a range here from -400 to 250 roughly of phi. That's not good. My actual phi should lie between -10 and 10, right? Outside there, I'm not interested. So, but this is actually a nice thing to realize. I can do this continuation, and I don't care about the actual physical constraints of my problem. Mathematically, I can do what I like. So I have this whole family. It's a huge family, huge angles, huge velocities, but it's a single family of right grazing and a single family of left grazing orbits. And now I do a post-processing step, and I'm just going to take those segments of this family that satisfy that phi is between -10 and 10 for the whole duration up to the moment of grazing. Okay? If you're reading this last bit, those I have not taken out. So there are, of course, orbits that graze and then later will leave after all. I'm not calculating those, so I don't know where they are. But when I take my segments just as the solution that stays inside -10, 10, I'm getting this. I have a fantastic curve boundary here and something a little more complicated over there. So let's zoom in. And what I'm seeing here, I guess the color difference is not so good in this projection. I have a dark brown, which is right, and a more orangey brown, which is left. Not sure if you can see that, but there's a curve running here, which is right grazing, and then there's another curve here, which is left grazing, and then I'm getting a right grazing again, and a left grazing again, and then another right grazing, and another left grazing, and then it actually stops. I don't come back again. But I can see that my boundary from the safe regime is actually composed by segments of alternating left and right grazing orbit families. And I'm calculating them. I'm calculating a little bit extra. And these are the ones that graze and then leave. I've taken out the ones that leave and then graze. Those I can find easily. And then I was thinking, well, is this useful information? It actually is.
So just why would it be asymmetrical? The response looks symmetrical.
Ah, yeah. Yeah, it's a bit tricky. So my system is actually symmetrical, but my force has a different symmetry. So if I would make this picture not in the slice t equals 0, but in the slice t equal pi over omega, then you would see the symmetrical copy. Okay? So what I now did was say, okay, all I want to know, instead of the time that I leave, let's see if I leave through +10 or I leave through -10. I use two colors, green and blue. And now you can see the meaning of these left and right grazing curves in the colored regime. They're actually giving me a discontinuity in the function of the time it takes that I leave. If I miss +10, it's going to take a while before I leave through -10. And if I then graze over here, it's going to take another while before I leave through +10, if I were to leave at all. And so I get a very nice structure by just this one computation of two families of left and right grazing orbits. Okay, so to end, let's show a bit more of what's going on. There is a lot of exciting dynamics going on here if I just vary the forcing amplitude. So again, my earthquake is a sine wave. I have my frequency fixed, and I'm changing A. So A is 0.6. This is the picture we already saw. Now I'm increasing A. I'm not going to be very audacious. I'm just going from 0.6 to 0.61. And what I see is I'm getting more curves, more alternations, and I see a development of what I call fingers in my phase plane. And if I change A ever so slightly, third decimal place, 0.611, boom, I get a fantastic transition where my fingers are now, boom, all the way over across to the plus 10 boundary, and I have split my region into what I first thought were two, but actually the white here is also actual a hole. I was thinking maybe we haven't calculated it far enough in time, but there are more holes here than just two. And then I can go up 0.62, and this thing closes up, and there's some other stuff happening. And then 0.62, I already am way into this transition, and I see that my fingers have gone and filled up an entire regime, and now I do have two regions where I'm safe, but there's a lot of colors here. I can go further with A and actually close up more or less this hole eventually. But yeah, I haven't shown that. So, I guess let me conclude a little bit here. What I've been trying to convey to you is that two-point boundary value problems are the coolest thing on earth. You should continue in using Auto or your favorite package, and you can compute absolutely everything you would like. Anything is essentially a two-point boundary value problem. Now this is cool because there is a whole theory about existence of solutions for ordinary differential equations. Smoothness results, the whole works carries over. So we have a numerical setup that is well posed, tells me exactly what I'm going to find, what the smoothness is of my solution. And so I know a lot more about the system just by doing continuation. Now, one fun thing, and I haven't really touched upon that here, but did, for example, in the scientific computation seminar on Monday, is that you can use this to go outside where the theory of manifolds or whatever the application is. On Monday it was the slow manifolds theory and the organization mixed mode oscillations. You can take your computation outside of that realm because the numerical analysis is sound. Everything's well posed. You are calculating something that's really there. It's just that the interpretation of your solution family might not be the object that you thought you were approximating. But you were finding the solution family is all right. So you can really take this into a regime where the theory is not quite complete yet, and you can use it to explore numerically what it is that you might like to prove. Now, on the bottom here, I just wanted to show that I was really there. And it was really exciting, because if you're an invited speaker, you get to sit in the front block by the podium when they hand out the Fields medals. So my tiny camera could actually capture the Fields medalists and the event of Ingrid Dobshi congratulating Mariam Mirzakhani, which I thought was the coolest thing, that I was actually there when the first female Fields medalist is presented with her award. And so then took this picture. That was me giving the talk. And this is a good friend of ours, Marcelo Viana, who's going to organize the next ICM. So thank you very much for your attention. Yes.
Can you remind me what A was in the previous set of...
A was the amplitude of sine wave of the earthquake.
Okay.
So, yeah, I mean, the real fun in this setup is, of course, that you'd like to step away from this nice earthquake that's a sine wave. You just want to use a real earthquake, perhaps, or something that is a mathematical stylized earthquake. That would be the essential earthquake to use to see how safe your building actually is. Yes?
In your neuron model,
Yes.
You raised the potential, and you did a different differential equation with a new sink
Yes.
that your solution was being attracted to.
Yeah.
That new sink, if you follow it continuously by decreasing the voltage,
Mhm.
which sink does it become? Does it become the lower sink, or does it become the upper sink?
Okay, so when I say that I need to have a strong enough applied current, it means that the sink that I would get if I would follow this one has undergone a fold. So for the applied current that I'm applying here, it needs to be strong enough so that I lose the, say, brother of this one. And I'm only left with the one that sits roughly here, which is the brother of that one. So if I were to follow and I take the sink that I have for this applied current and take the applied current down to 0, I would end up at this point.
You would think then that raising the current quite high and then decreasing it slowly would put you right into the basin that you're interested in.
That's what you would think. But that's not what's happening.
Why
Because if I would raise the current high enough, okay, so then I would have to hold it for a long time, that I know I'm close to this one. And then if I would slowly decrease my applied current, that sounds like a very complicated protocol, but yeah, that would be possible, that you first wait for a very long time.
What do you think a very long time is in this case? How strongly attracting are these things? We were talking about periods like half
Well,
a second.
let's say, let's put it this way. If you have a neuron cell that is alive and you are putting the voltage up, what happens is calcium is coming into the cell. This kills the cell. So if you do it for too long, your cell is dead before it starts bursting again. So you need to think of long enough as being a time that the cell is still painfully alive with all this calcium and is about to flush the calcium. And so now I'm thinking two things at the same time. So long is 15 milliseconds or so in this context. You don't really want to hold it for a lot longer. And so you could think of holding it for maybe 10 or so, get to what you think is your equilibrium, and then quickly bring it back to hope that it tracks that equilibrium well enough that you're in the upper state. You don't have to go all the way to this equilibrium. As long as you're inside the basin, should be good enough. And so you could think of it as a protocol, but it would be a tricky one because it takes longer to achieve. I'm trying to come up with the minimum time for your strength. But it is indeed another idea to do it that way.
Hinke,
Yes.
I lost. What is the relation between invariant manifolds and the last part related to earthquakes?
Yeah. What I was saying here in terms of the actual computational setup, I'm calculating. I mean, I had this question when I was defending my PhD thesis. I was computing invariant manifolds, and I was thinking invariant torus or something nice like that. But then I got this question, like, well, if I just take an initial condition and I integrate it for a while, I have a trajectory. Isn't that an invariant manifold? And I couldn't answer yes or no. But now I know. I should have said yes.
Yes.
It is. It's a finite time invariant manifold. You know, if you only want to integrate from 0 to a particular time, then there is some tricky business there. But this is an invariant manifold in the sense that it is a family of solutions of the vector field that has a special property. But the main thing that I find the connection is because the way I calculate it is the same two-point boundary value problem setup that I would use for calculating a stable or unstable manifold. Now another fun thing, and that is something that I didn't touch on at all, but this transition has to do with the fact that I have a sinusoidal earthquake. there is actually a periodic orbit in this system, because if I have periodic forcing, I have periodic solutions. And there is a saddle periodic orbit that sits about here. It has an unstable manifold that you can see would probably go roughly here, because I have just had my grazing family interact with an actual unstable manifold. That's something that I haven't got the pictures of yet, but that I really want to work on next. Because that's a very interesting mix of the non-autonomous aspects and the actual invariant manifold theory. Yes?
So, this is related to the previous question. When you were discussing the stable and unstable two-dimensional manifolds of the saddle equilibria, and you were describing your method and Cais-Doodle's method for this, the difference originally was that Cais was using a much larger point boundary with a problem, going from the small set in the eigenspace all the way to the arc length you're interested in, whereas you guys were doing it incrementally.
This is geodesic level sets, yes.
Are you using the same for your second example, or are you using really just raw auto? Are you using
So
geodesic level
here,
sets in
these
your
computations are done using geodesic level set,
The
which
other one?
you could use, Savius's approach or your own approach for calculating this manifold in principle. And these grazing families here are computed using auto raw, because I have the setup that my entire solution starts in t equals 0 and ends at a grazing point. And so, I wouldn't see how to think in some geodesic level set approach to that. But
I guess the logical continuation to my question is, what's the advantage of one versus the other, if both of them are applicable?
The advantage of the geodesic level set method is that what you're ending up with is a mesh that is suitable for visualization immediately. Here I need to do a post-processing step. If you compute an invariant manifold using Savius's approach of just getting the whole thing as a family of of a single orbit segment, if you want, then you would need to do a post-processing step often to get a good surface out of it. So it's harder to visualize the computation, but
in terms of accuracy and efficiency, you would say both approaches are comparable?
We haven't really compared the accuracy, because what you're doing is you just have accuracy settings that are not the same for the two approaches. So when you do the geodesic level set method, we have an actual proof of that the accuracy is, that you have a convergence argument that when you reduce the mesh, you will converge to the real thing. And that is all assuming that the actual boundary value problem continuation to find the next point is done at an accuracy that is higher locally than the error that you've made so far. So it becomes part of the interpolation error if you want. So with Savius's method of doing the whole thing in one go, you were talking about the actual accuracy of the boundary value problem, which is, of course, for the bigger object, not as good as the local problem that we are solving each time. And so I would say that both methods at this stage are equally accurate, because the pictures that Bernd showed, for example, last week on Thursday, had level set method manifolds and direct curves in the plane that were calculated using Savius's approach, and they're spot on. But who knows? Maybe one is slightly more accurate than the other in the 10 to the minus 5 realm or so.
Just one other question about the frame. So do you have any understanding what the resonant frequency is of the structure by itself? And how, because then it would tell you how A relates to sort of like the intrinsic.
Okay, so I didn't really say that, but this omega is also scaled. It's scaled by the resonance frequency. And so 1 would be the linear resonance, but the nonlinearity of this mu function pulls that resonance term over, and the 0575 value that I'm using is in the middle of that term. So I have 2 attracting periodic states that I also haven't mentioned.